Great. Good morning, everyone. Thank you for joining. My name's John Wiley. I'm the Managing Director of DataSparQ. Here at DataSparQ, we build intelligent products combining data science and design to actually help businesses and their users and their employees really take advantage of the power that artificial intelligence and machine learning can offer. With me today are Gareth and Alexei. Gareth is our Head of Data Science, and Alexei is one of our Principal Data Scientists. And today we're going to talk to you about some of the work we've done, some of the products we've built in the fraud detection space and insurance. Both Gareth and Alexei have a wealth of experience in this field, and today we want to share some of that with you. Before we get started, I just want to let you know that you can ask questions throughout this webinar. We'll take a chance to answer them as we go. Some we might leave to the end. You'll find the little questions box in the Zoom application. So please pepper us with questions if there's anything you'd like to know more about. And with that, I'll just get started and we'll hand over to Gareth and Alexei.
Okay, great. Thanks for joining, everybody, and thanks, John, for the intro. So a few things that we're going to try and address in this webinar, all around fraud detection, insurance industry. But what we'll start with is to talk about just a quick intro into data science, machine learning, and specifically how that can be applied in fraud detection. A quick kind of whistle-stop tour of some of the data sources we think are beneficial in supporting the effective feature engineering for fraud detection or support fraud detection in machine learning. A few of the modeling approaches that are available and what are some of the considerations in selecting the appropriate one for specific cases or creating ensembles. Talking about a little bit about the training and testing techniques that we use in general, but also some that are quite specific to detection, to cases like fraud detection. And then talking quickly about how we realize benefits in both the short and long term from fraud detection solutions. So quickly, let's just talk about the problem. And I think all of you are probably much more aware of this than even ourselves. But in 2016, there's one of these studies from ABI talking about the number of dishonest insurance claims that were identified and the value associated with that. So 125,000-ish claims valued at about 1.3 billion, and they were the ones that were identified. But the estimate is that there's more than that are unidentified, that got unidentified. And of course, that's what we're really after, improving the ability to identify the previously undetected cases. And of course, the trickle-down effect is that impacts the risk levels of the insurance companies and therefore the policy, the costs for policyholders as well. And I think, Alexei, you were looking at this with regards to some of the insurance companies that we were working with, and you actually think that it might be higher than that, right?
Yeah. We actually explicitly confirm with through the work we've done with insurance companies and law firms which work in collaboration with insurance companies that this figure is the underestimation of this figure is at least of the factor of 2, because all the new kind of claims which we flagged for them newly discovered, there were at least twice many of them, and all which we flagged, they checked, were indeed confirmed by them that they were high risk and were in investigation.
Right.
Yeah.
Yeah. So I mean, and this, as we start to go through this, we'll talk about how we find those extra cases and specifically some of the techniques that we use to do that. A quick kind of tour of machine learning and maybe where fraud detection sits in this model. Machine learning we separate into 3 main classes. We've got unsupervised learning, supervised learning, and reinforcement learning. Unsupervised learning is typically where you let the data determine patterns itself rather than training it based on historic tagged or flagged cases. So if we think about fraud, then unsupervised learning could be looking for anomalies, anomalous patterns for claims that don't look normal, let's say, so outliers. So clustering allows us to find outliers. And we'll talk a bit about anomaly detection. Alexei will talk a bit in more detail about anomaly detection. In the supervised learning space, we've got classification and regression. and typically fraud detection lies in classification. And Alexi will talk about the different types of classification that allow us to find fraud or different types of fraud and things like that. The other type of supervised learning is regression. And typically here we're looking, so in regression, we're looking for a continuous variable, like a number, typically on a scale, so a time or a price or a risk score. And classification, we're looking to put elements into buckets. And then reinforcement learning is more about, so you can think about the AlphaGo kind of scenario where you're trying to train an algorithm based on trial and error experience and then rewarding or penalizing based on success or failure. So a question on the question board, where does risk modeling sit in this picture? Okay, so that's a difficult question because it's such a broad field, but maybe if we think about risk modeling from a risk at time of pricing policy perspective, so how do we calculate risk? So Alexi, where would you put that in this picture?
If it's at the inception time, right? It depends how the business is set up, but we can think about it as supervised learning, right? And regression, as you already mentioned, we can calculate the risk score depending on the factors which go into the policy application and then make a decision based on that number. Yeah.
Okay. Okay, so I think that's a kind of a simplified answer to that question, but I think the question is quite broad. So if we could, in the Q&A at the end, if we want to go in more detail into that question, we could probably sidestep to it. So machine learning is, there's a kind of a slide saying, when considering a use case for machine learning, what are the topics that we mostly look for, what are the kind of features of that problem that we look for to determine whether it's a good fit for machine learning, and does that work in the fraud case? So first thing is identifiable value. You'd be surprised how many people in the data science world build products or start to build products or build models when they don't necessarily know the value associated with the problem they're trying to solve. Fraud is an easy one, right? If we can detect fraud, then we don't have to, we can avoid paying out on a claim. This is immediate value realization. So also if we improve our rate of detection of fraud, we can reduce our risk. So both of these, I mean, this is quite a clear path to value. Other use cases are sometimes a bit more difficult.
Yeah, there is another side to identifiable value. So one thing is that we can detect high risk and stop paying on those claims if we reason to believe and can prove that it is indeed fraudulent claim. But on the other end of the spectrum, we can also identify the claims which are very likely low risk or no risk at all, and improve our ROI, as in not investigating them because we don't believe we can find among them any fraudulent claims, so we can save time and then manpower of not doing that on the spectrum as well. So that there is value on both ends, so to speak. Good
point. Make the fraud detection team more effective. Yeah, I think that's absolutely true. So the next is in looking for something that's good for data science. We look for a complex challenge, and by that I mean looking for a problem that requires a lot of information to solve it. A lot of different maybe data sets or features that could influence the decision of whether something falls into the class of what you're trying to identify or predict, and so much information that is difficult for a human to process. So those are the sort of cases that are really ideal for machine learning, because the models are able to work in a multi-dimensional space. If we think in 2, 3, 4, 5 dimensions from a data set perspective, the model can look in hundreds of dimensions, and so at the same time, and determine a kind of a score for a particular class, like a score for probability of risk. So fraud definitely has that, because as we'll see when we look a bit at the data sets, there's a load of data sets we can consider in trying to determine if something is likely to be fraudulent or not. The other thing is data. So having good quality and good length of history of data is really important, because that's how we especially assist in determining the temporal. So that the history is important for temporal trends. So if there's certain time-based trends, and just generally like good quality is important, because you don't want noise in your data, which is throwing in the wrong direction. And and a variety of data sources is important because it enables you to avoid biases which may be within your historic data. And of course, specifically for supervised learning, it's important to have historic cases where we have identified fraud in the past. So this is a useful guide for the model to tell it what fraud typically has looked like in the past. Now, Alexi will talk a bit more in a moment about the classification problem versus the anomaly detection problem, because of course we haven't seen all classes of fraud. There might be stuff getting through that we've missed, and so that's why the anomaly detection or the clustering technique is quite also valuable. And from a product development process perspective, I think this is quite important for anyone developing a fraud detection solution within an insurance business or outside to go to market with it, is to follow a sort of iterative agile development process and then a DevOps continuous development process following on. So we build our MVPs using this kind of agile process, and then we continuously enhance those solutions with the DevOps process. I recommend anyone building a fraud solution or building any product or solution in this space of machine learning should follow these approaches, because it allows you to get to a product quickly that you can test in a real live environment and then continuously improve on it. It's just the core of Agile and DevOps and all the benefits associated with it. And of course, the ownership of a solution like this typically sits in the fraud detection team. So a fraud detection solution should be owned by the fraud detection team, and they should be driving its development. So these are the processes that we follow. A lot of people have variants on these, but this is the path that we follow. And if anyone has questions on these things,
just to answer that, it's also worth noticing before we talk about the data, a machine learning model can always get better. We can always use new data sources, create better features. And so if you believe that a machine learning model will always get better and become more accurate, well, you're not going to always wait for a slightly better model next week. So this agile approach allows you to take advantage of what you have today, but then incrementally throughout every sprint, look at how your model is performing to drive further improvement, so you can continually iterate and improve the level of fraud you detect.
Good point. I think when we're inside of an organization trying to build a product, so inside of an insurance company trying to build a fraud detection product, and the important thing is to get value quickly, because generally you have a limited budget to enable you to build your first product. So that's why we go down this MVP approach, so minimum viable product approach, where we build something quickly, get it working, show that it's got value associated with it, and then iteratively improve it and make it better and better as we spend more time on it. So I think so now that's a sort of general overview, but I'll hand over to Alexi to talk a bit more about the actual types of frauds that we're looking for and the techniques that we follow, both in a product development perspective, but also in kind of classifying the challenge a little bit. So Alexi, do you want to talk a bit about these things?
Yep, thanks. So we typically have two approaches to finding the fraud, finding fraudulent cases or ranking the cases by high versus low risk. First is based on analyzing known patterns. So we base kind of solution on analyzing data of the historical cases, right? The cases which were previously triggered, flagged, and investigated as fraudulent and confirmed as fraudulent. So in the historical data, both in historical data, and then as we test the solution in the new coming data, we look for the cases which kind of display similar patterns of behavior, and similar patterns is an important kind of keyword here. We don't necessarily look for exact matches for, say, rigid thresholds on a given parameter. We're looking at tendencies, right? If let's take a trivial example. If there is a filter that case is committed, I don't know, say after 11 p.m. Close to midnight, kind of, or indeed in early hours of the night, are more likely fraudulent, simply because that's where there are fewer witnesses and all these kind of things. So historically, we may see this pattern. Instead of looking for a kind of threshold at 11 p.m., we consider all values, right? We're looking at the difference of 10 p.m. versus 3 p.m. of midnight, indeed, or 1 a.m. So we're looking at the trend. We're looking at where there is a higher chance for a fraud to happen versus lower chance. So this is known patterns, and then kind of expanding a little bit more on these hard thresholds, which is probably decision trees solutions, kind of classical approach in the past. We look at many more variables through machine learning approach, and that allows us to look at more subtle indications of fraud, right? And then if we have multiple variables, multiple features of the data pointing in the direction of the fraud, even if each of these dimensions, if each of these features are kind of subtle in its own right, if many of them are pointing in the direction of the fraud, that allows us to potentially trigger a case and send it into the triage team for investigation. So this is about known patterns. I'm looking for similarities in data to known patterns or kind of tendencies towards known patterns. Of course, very importantly, it's also look at the unknown patterns. So basically what we are looking is at the significant difference in behavior which we could consider normal, right? We will discuss it on the following slides in a little bit more details, but we can look, for example, at clustering techniques when we look at the in multidimensional space of the features of the cases. We look at the behavior which is not typical potentially to the cases which previously were labeled good or potentially risky, and then if you find this kind of separate clouds, so to speak, of cases, we can investigate them and potentially find new kinds of fraud which we didn't suspect previously or didn't investigate historically. So it's important to keep in mind that fraudsters, or many of them, are also smart people, and they continuously come up with new ways to kind of get away with it.
So before we move on, there was one question in the chat, which was around, before we get too far away from the MVP conversation, about how long it takes to build MVPs. So, I mean, typically we would be trying to build an MVP within 10 to 12 weeks. Now, it depends on the complexity of the use case you're trying to solve, and it depends on the, let's say, the maturity of an existing solution which we're trying to improve on. So, yeah, we say 10 to 12 weeks kind of is a good amount of time to give yourself, but I think it's quite dependent on what space you're trying to address. And I think the important thing, and we'll talk about it a bit later as well, but is that in building your MVP, it's often a good idea to build on a subset of your space, right? So if you're treating many different types of insurance, so motor and personal injury and life and something, to look at one area of that, and maybe to look at one geography, so one country perhaps is a good. So create a subset that you're going to address in developing your MVP to let you test and the logic, and then test the solution against live cases, and then to expand from there. So in that first MVP development, give yourself something manageable.
And I think it's just worth adding, when we say MVP, we really do mean MVP and not a pilot. We want the MVP to be something you can actually use in the real world, that's going to try and make some impact on value for you, not just an historical theoretical exercise on historical data only. We want to design the MVP that means you get something that's operationally useful.
Yeah. And kind of to draw a little bit, one more comment on this, and draw from specific examples of use cases when we work. One example is with insurance company, where we delivered a solution which paid for itself 7 times over within 2 months of building that initial MVP. So that's one example. For the other example, there was also, I think it was for in the time span of less than 2 months, we delivered a solution which was able to detect twice more cases and then trigger them for investigation. And within those 2 months, they spot checked the additional claims we triggered for them, and every single one of them, they confirmed that it was worthy investigation and should have been discovered. So that was another example, which was less than 2 months. And finally, with life insurance company, the solution we built, the example was a little bit less than 3 months. It took us to the initial MVP. And of course, life insurance is some of the most complex cases because there is a lot of unstructured data, a lot of complexity in the decision trees there. So those are 3 examples, for example, from our recent work. Okay, so going forward for a little bit more in details for classification, of course, these are just simplified examples. Binary classification can be, it can be, what we're discussing here is detecting fraud versus non-fraud. And then if we detect, for example, potentially fraudulent case, and we have different classes of those or different level of severity, because on that our actions may depend. We can also consider multi-class classification and split the claims into different classes and different types of fraud potentially.
Yeah, and even when Alexei is talking about binary classification, it's a score. So if you imagine the space between those 2 clusters as being, well, number one, not just in 2 dimensions, but in hundreds of dimensions, but also it's a distance. So how far am I towards something that looks more like a red X than a blue circle?
Yeah, absolutely. Because we typically don't see picture which is so perfectly split, right? So then we're talking about degree and the level of risk.
Yeah.
And this is a slide on kind of in a little bit more details on anomaly detection with a few illustration. Basically, what we are looking and these illustrations, of course, are 2-dimensional because that's how we can put it on the slide. But basically what we're talking about is when we are looking in multi-dimensional space of features, right? It could be age, number of cars involved, hour of the day, whether there were witnesses or not. All these dimensions building up, we can have dozens or hundreds of them. And then we're looking at standalone clusters of behavior which were not in the past associated with kind of fraudulent or non-fraudulent behavior. And if they're standalone from either good or bad historical cases, that's something which could potentially be worthy of investigation and typically yields results. Yeah. So that's quite an extensive potentially topic to discuss, but just a few highlights on typical sources of data which we are considering when we build fraud detection solution. Well, obviously there should be accident description data, and the more detailed it is, the kind of easier it is to build accurate solution. The data on all the participants of the accidents, and that's not just about the people who claiming, but also potentially witnesses, medical, if there is any hospital was involved or any medical kind of summaries on the case, any experts otherwise involved in the case, and we can supplement the data on these people who participated in the accident one way or the other, also with publicly available information like census data, for example, or kind of data which is not necessarily publicly available but could be made available for the solution, like mosaic data, from which we could imply, for example, affluence or over a given area where people live or where accidents happen. Those we find useful for often useful for prediction. And then data on the vehicle, police data, and when we're talking about police data, we can talk about police data specific to the accident, as well as general or public information from police, as in, for example, density of accidents in a given area. and we can build quite complex metrics out of this data. We can look at the density of the accidents within specific radius around the place where accident happened, or maybe indeed around home addresses or of claimants. Also worthy mentioning here, and it's actually true for many of the data sources, parts or the whole data source, specific data source could come in an unstructured way, as for example PDF documents or handwritten documents, things like that. So we have the ability through natural language processing to analyze the data, build features on top of that, and include it into the case. Oftentimes we actually find that data which comes from unstructured field, a life insurance case is actually maybe one of the best examples for it, because there are a lot of fields which are not structured, where people supplement their application, for example, with a lot of additional data, with a lot of additional comments. Analyzing that unstructured data, we can extract many more features, and often stronger features than structured data allows us to see. So that's very important.
Yeah, and we have we have a question in the Q&A sections, which asks, how do you determine what are the best data sets to use? I think so. It says external data, for example. So I think the question there is on external, and it's a good question. I think because the examples on the screen are largely related to motor and personal injury, and different data sets are relevant for different obviously fields of insurance or different classes of insurance. But I think one thing is, when we talked earlier about the process of developing MVP, in that kind of iterative process and in the DevOps process, there is this element of developing hypotheses. So as an individual within the product team comes up with the suggestion of additional data sets to use, there's kind of this development of, okay, what is the hypothesis? The hypothesis is that information could somehow assist you in determining if something is fraudulent. There's a lot of data sets out there, of course, which are completely irrelevant, so you've got to be quite clever in the ones that you want to test. But then there is this approach of, well, developing features on it and then testing the features, right? So we can do a feature ranking or features, So I think it's a big question, because there are so many options of data sets to use, that most of the data sets that we consider and are on the screen at the moment are data sets that typically would be used by the fraud investigators anyway, and it's more about developing, well, number one, using that information in a very granular way, and then number two, using it all together. So the small indications, and as Alexia was mentioning earlier, slight indications in the direction of fraud on many features add up to a score which could be quite high, which an individual looking at the data separately may miss, because it's only a slight push in the right direction. But yeah, then because when you develop the model, you want to find the features that most strongly indicate that a case may be fraudulent. So we go through a process of feature engineering first, and then feature selection. So yeah, there is a kind of a process, but in figuring out which data sets are most relevant, that will be part of the hypothesis process, led by the product team, who are focused on developing the product and identifying the data sets. So,
yep. There is another question in the chat about AFR data. We don't typically we don't own this data. We typically have it indeed accessed through insurer clients through their data sets, through their access.
Yeah, I think the important thing here is everything we're talking about are products that we build for insurers, right? So this is not a developed product that we sell off the shelf. It is actually a product that we develop with insurers. So it's bespoke product development for individuals. Of course, we have reference models and reference deployment architectures, and I'm going to talk about that in a moment. But this is not an off-the-shelf product. This is a tailored product we would develop with and for you, but based on all of our historic knowledge and using all of our historic templates to kind of accelerate the development process. but we would develop it with you based on your data if we were doing it for you. And if your internal team are developing this themselves, then that's the same approach they would use. They would use all of your data and your access. So we're not an insurance company, so we typically don't have access to that.
Yeah, maybe one more thing worth mentioning on this slide before we move on to the next one is that when we use the data, we also often engineer quite complex features to enhance their predictive power for, say, predicting fraudulent cases. And one of the things which worth considering is when a single individual case may not necessarily justify investigation, the sequence of the cases which are connected in one way or the other may indeed kind of trigger an investigation, right? There was just recently, I think a couple of days ago, an article in Times when they were highlighting the results of the multiple years investigation on the group of individuals. More than 150 individuals, I think, was mentioned in the paper, which were involved in the scheming and fraud cases, multiple fraud cases connected to each other. So kind of keeping in mind not just kind of in-depth investigation of every single claim, but also potential quote-unquote interactions between the cases, so that we can discover the multiple case patterns. That's another thing which we do when we build such solutions.
Yeah, good point. I think that it was on one of the earlier slides, but we didn't maybe call it out that it's fraud is not just looked at on a single case basis, but also on groups of cases that may be interrelated.
Okay, we mentioned NLP already on the previous slide quite a bit, just a few more kind of details here, and we will provide this slide so you can look through the details a little bit more at your leisure. So when we look at the NLP building features based on natural language processing, we look, for example, for specific words or terms or combinations of words which could discriminate between potentially fraudulent cases versus non-fraudulent when we analyze documents associated with a case, or indeed whatever comments and descriptions associated with the case. We can also look not just for specific obvious keywords, but kind of context words which may indicate differences. We look at the patterns of language, right? It could be as trivial as lengthier comments maybe attributed more often to fraudulent cases, for example. It's just a trivial comment, not necessarily true, but looking at the differences in pattern of language, length of sentences, words used, and all that can indicate one way or the other. And even more trivial potentially things like spelling and grammar, and then counting number of errors, especially if the document is not expected to have errors and supposedly is coming from a company and should be well verified and checked and all that. If you notice these things, we can check the propensity of such a document to indicate that it is a potential fraud. Yeah.
I think there's a lot of different, and in NLP again is quite a big topic, but specifically relating to an individual class of insurance, you can imagine quite easily developing these language ontologies or language kind of hierarchies or reference or synonyms for the same terms, and looking at how those different terms indicate again a tendency towards fraud or not. And like we've been saying in the earlier slide, it's a combination of those features and lots of other features that bring us in that direction of determining whether in that multidimensional space how close we are to, are we closer to fraud or are we closer to non-fraud?
Yeah. Oh, that's talking about data, maybe finishing on the topic of data. This is responsible data usage. Kind of example, one of the most recent examples, you can see the date on the article submitted 10th of April this year. So this is about accessing the Google Street View imagery for cases, and the authors of the paper claiming that they can indeed improve the accuracy on the investigation of cases. Of course, with access to more detailed data comes responsibility, right? We always think when we build the solutions for our clients, we always think about whether it is ethical and to use one data source versus the other, right? The authors of this specific paper themselves, even in the abstract, you can see that they mentioned that there are potential issues with this because looking at the imagery, you can create proxy for ethnicity or religion or other sensitive data, which you don't want necessarily to use in your solution. So it's very important to have these considerations in mind when you consider one data source or another.
Yeah, we sort of in a kind of jokey way talk about the Daily Mail test, but it's a good way to check if what you're doing is sensible. If this was on the front page of the Daily Mail, would it be a good story or a bad? Well, they're never good stories, are they? But do you want that headline to be about what you're building or what you're using? If the answer is no, then just probably don't do it. But this is when we saw this first, this was our reaction was this seems like something that we probably wouldn't want to be doing because of the biases it might perpetuate, or even just the message that it sends out that using this data might maybe be socially irresponsible.
You may remember also from the recent years, actually, I don't remember whether it was actually Daily Mail or some other newspaper which was mentioning an investigation done where people were checking the difference in the insurance policy prices, where just different names were used and otherwise the same application, and that was obviously a quite scandalous.
The Muhammad test.
Yeah.
Mo Compare, I think, was the title.
Yeah. Okay, so going into a little bit more details and in particular how we build solutions for fraud detection. First, we start with checking all the data against biases and things which we may potentially want to exclude, like, well, gender is one of the most trivial and simple examples to understand. So we filter data and exclude potential fields which we don't want to use. But then we did mention time dependency. And for fraud, it may be more relevant than for many other solutions because the way fraud is committed is continuously evolving. So we want to potentially, for example, give a higher weight to the cases which were investigated more recently so that our model kind of keeps up to date through this weighting. So we arrive to filter data set, and then we split that filtered data in multiple streams. One of the streams, which is marked with number 1 here, is we take part of the data and use it for training and testing. So training obviously is where we introduce the features trying to improve the performance and accuracy of our predictions, to splitting the cases into fraudulent, non-fraudulent. And at every iteration, we do the test against the testing part of the data so that we ensure that we don't introduce any overfitting, we don't introduce any heavy bias, and we make sure that the solution which we build would generalize. So after multiple iterations of this, we arrive to a machine learning model version, at which step, or at every step actually, in those iterations, we also consider feature importance list, which serves in kind of multiple ways. Two of the important ways is that we can see kind of predictive power of every individual feature and potentially exclude features which don't contribute, kind of only create potentially noise. But also we can see if any standout features and if any features stand out in the way which is significantly more than we expect, and therefore could be potential biases or even wrong data to be included. So we have an extra control at this stage. Okay, once we train and test the model, we put it into the next step, step 2, with the quote-unquote final version, at least at this stage of the model, which we test against validation data set, which was the final third part of the data, filtered data. We split into, and validation data is the part of the data which the model have never seen before at the testing training stage yet. So this is the kind of final verification against any biases which could be potentially introduced in the previous steps when we optimize the algorithms. And it's completely quote-unquote blind test at this stage. And it's this stage from which we report the performance of the solution we built. And finally, the third stage is once we're done with training of the model on, say, historical data, we put the model through the control test, through live data test, as in new cases are coming in, and then we can split them, for example, into two streams, A and B, one of which we can send through machine learning solution and the other through old approach, and then we can compare the two, or indeed complement the two approaches with each other. Yeah.
I think one thing that, as Alexi was going through this, I kind of realized that we didn't mention when we were talking about the product development process is that the idea that machine learning or that data science should be a black box, we specifically don't agree with. So when we're developing the solutions, we do like to develop with the people who will use the solutions and open up the box and show them how it works. In the models that we've been building for fraud detection, most recently, we've been developing an output, which we'll talk about in a couple of minutes anyway, but it's a scorecard that tells you all of the features in that multi-dimensional feature space. So all of those data features that have most influenced an individual's case to be flagged as being high risk. So was it the type of car, if it's in motor insurance? Was it some of the natural language? Was it some of the time of day? What were the features that drew us little by little towards determining that a high score? And we published that so that this means that the investigator is able to actually have a direction or an indication of why the model thought the case was fraudulent and therefore how they should maybe target their investigation. So that was just kind of to remind myself that that we try not to develop products in this space that are black boxes. I don't think that really works for anybody.
Yep. And so on this slide, we showed that the typical output, this is at the initial stages of the building the MVP solution, and for real fraud detection solution, which we're building, which splits, in this case, historical data. Therefore, we're able to highlight it in red or blue as in fraudulent cases versus non-fraudulent, historically identified as fraudulent or non-fraudulent cases. And we can see how model was performing against those. You can see the split. There are some peaks at the end of each end of the spectrum, which indicates that in this area, it's very unlikely, for example, in the red area on the left, it's very unlikely that those cases will be clear, so that they should be investigated. And on the other hand, on the on the right-hand side, very highly accurate definition of the cases, which would be clean. Also interesting to note here that, of course, that the solutions are rarely perfectly split the two, but more importantly, that they don't necessarily do it for kind of wrong reasons. They don't perfectly split the two classes. Thank you. Simply because actually historically the cases were missed. Right, when we do it in real life, and when we build the solutions and report, for example, the quote-unquote blue cases, the clear cases, which were historically indicated as clear, and they received very low score from machine learning solution to indicate that they actually should be suspected of fraud. And when our clients would check those cases, they would indeed confirm that more often than not that those cases were missed in the process, and they justify investigation, and after investigation they often would confirm that they were fraudulent cases. So that tail which goes to the left, for example, from the blue class, and then under the red peak is not necessarily that the model was wrong. It actually is indeed the benefit of using of the model, that it could find more subtle patterns which indicate that those cases were fraudulent and they need to be investigated. So that's exactly the illustration of the strengths of machine learning approach.
Yeah, and I think actually it might be on the next slide, but yeah, so that sort of plays to this slide, which talks about benefit realization. So the graph on the previous slide was looking at all historical cases, claims cases over time, and how the model would have classified them if it was classifying them. fraudulent or non-fraudulent and how far on the spectrum they would be. And as Lexi was saying, as you start to build the first version of the product and you train it over all the historical data, and then you score all the test data, you can score all the data, then you start to see cases that the model thinks are fraudulent, like Lexi was saying, but actually you historically did not think they were. If you still have the opportunity to investigate those cases, then there's your quick win, right? That's your immediate value realization, because you investigate those cases that the model thinks is fraudulent, but you historically thought were fine, and then you can gain immediate value from them. And they could be cases that were, just in the past, couple of weeks, a couple of months, whatever. You still have the ability to go back and get money from, or if they're high value, you can probably go back a lot further. And that's tactical value realization out of the MVP, even during the development phase. That's even before you get to your live test. So within your kind of 12-week development of your MVP, you should be identifying cases that the model thinks are fraudulent and that you should investigate, because there's an opportunity to prevent some payments. Of course, more importantly and more strategically is the continuous value realization. So embedding the solution, the product, inside of your business process. So how does your fraud detection department currently work? Your investigators, how do they work? And what are the tools that they use? How are cases scored as from a fraud propensity or probability perspective? So embedding the solution into your business process is key. And actually, at the very beginning of developing the MVP, you should be thinking, how am I going to embed this in the business process, and therefore how should it be designed? Because I want to either integrate with something, or I want to create a front end, or I want to create an application that's used by the investigation team that triggers or assists in that process in identifying fraud. So product development should always start in that design thinking phase of how should this be used in the business, in the business process, to realize value on every single case. And that's the whole product development mentality. Another thing that we always think about in again the product development mentality is that we want to be able to create champion and challenger models. So if we think about if we're in a large insurance organization and we have many different classes of insurance, and we want to test some models on all insurance cases and some models on specific ones, we want to develop a new model which incorporates new data features and put it in a competition against other models. We should develop a process and an architecture that allows us to do that. So we want to be able to have models competing against each other, so that we can determine which ones are acting or are performing best. And we want to develop, we want to make sure that we have a framework, an architectural framework that allows us to do that. I want to have 3 models live, and I want to direct traffic amongst those 3 different models. Yeah. So that's really important here. So new models can incorporate new features or new modeling approaches and be tested against the reigning champion in a specific area of the insurance space, but within the company on the same architecture. Question: when you have your solution live, what do you need to do to keep it working? Yeah, good question. So importantly, any machine learning solution that you have in production should have value. If it doesn't have value, then you shouldn't have it in there. But because it has value, it has risk. Because if you're realizing value in normal times, as soon as it stops working, you start losing value. So you need to do a few things. One of the most important things is monitoring. So you need to monitor your entire product, your entire solution, so that you monitor that the data is all flowing to the model. You monitor that that data is correct and that the quality is maintained. You monitor that your training pipeline that you've scheduled or that you have running based on some sort of specific criteria is retraining the model on a periodic basis. You monitor that the model is being consumed the performance from a speed perspective. If you're consuming that model through an API is appropriate based on the SLA, so it's getting pinged for a response and it's sending a score back as quickly as you'd want it to. And then also, very importantly, the performance of the model. How much fraud is it detecting? What's the rate of fraud it's detecting? Is that rate decreasing? If it's decreasing, what activities should be taken? Should it trigger the training pipeline? Should it do something else. If it's degrading and the built-in safeguards aren't getting it back up to performance, then how do you as a product team intervene and change the model, run some champion challenger tests, add some data sets, create some new features, or whatever is required to get it performance again. So monitoring is really important. In having a solution live, the important thing is to make sure that you've got resilience within that solution from an architectural perspective, but also in elasticity. So if you have a fraud detection solution working for, let's say, one country that you're working on and maybe one class of insurance, just motor or whatever, and you want to kind of start creating champion challengers that you're going to run across a whole of your sort of geographical coverage and all of your insurance space, then naturally your demand on that product is going to change. So if you have not got an elastic kind of infrastructure underpinning so an elastic API, elastic deployment approach, then at that point you will need to put one in. So usually good to consider that up front to make sure that you have that elasticity built in if you intend to evolve the product. But sometimes that is a bit too much effort when you're doing the MVP and you decide for MVP, we won't put in elasticity, but then we will afterwards. And yeah, I mean, I think just that champion challenger thing, just making sure that you as a product team can iterate the product is the most important thing. And then, yeah, so this is what I was mentioning a little bit earlier was when you built your fraud detector model, that's not the solution. The solution and the MVP consists of the fraud detector plus its consumption endpoint. So that could be a front-end user interface that is created, and there's an example of one on the screen, but that's used by a case management team, or it might integrate with the case management system. So if when you're designing your MVP, you decide, and this is it's kind of typical case, that every claim that comes in to the case management system is sent through the API to the fraud detector for a score, and then it responds with a score for that case, and then that triggers some sort of event in the case management system, which puts it into a specific workflow. Then then that's what you should be considering from day one. And when you develop your MVP, that's what you need to develop. You need to develop the detector, but also its consumption endpoint and its integration. In your MVP, that might look a bit different from what you plan to have in your future state product, but at least you need to consider that from day one. So so making sure that from a design perspective, you consider who's going to use it and how they're going to use it, and of course how you're going to realize the value from it. So however it's being used, you should be able to identify how will that give me value in the final solution. So a question on the chat: what's your typical ongoing cost model? Volume, annual, license-based, or transactional? Well, so as we said earlier, this is so shared value is a preferred model. So that's the easiest way for us to realize benefits, because then we own essentially the enhancement of the product continuously for an organization. But we have different models that we can, from a commercial perspective, can discuss. So we can, so I think that's a question that we can maybe take offline, because this is, again, we say this is not an off-the-shelf licensed product. That's not how it works. We develop products for organizations that need sort of bespoke performance and products tailored to their needs. So and if you were developing this internally, it's like you having an internal team, but essentially we work on just the product. And yeah, different, so value shares is typically a good model, but there are other options too. So I think that was it from this one, and then I mean, I think that was the primary topics that we wanted to cover specifically related to this field. John, do you want to talk a bit about how we go about the process? Yeah,
thank you, Gareth. Thanks, Alexia. That was very, very good. Just to give you all on the phone a quick overview to actually how we build these products here at DataSpark. As Gareth said, we want to make sure we're building products for you that are solving high value problems, and we very much believe that to do this, data science is a team sport. So it's not just the Gareth and Alexis that help solve this, but it's actually combining the data scientists with the technologists who can make sure these products are elastic, that they're scalable, that they're robust, that we can easily take it beyond the MVP and into something that's going to be resilient in your business. But we also couple that with some design thinking, product design thinking, to make sure we're really considering how these models are going to be consumed in your business. On that previous slide, we showed that there might be one endpoint, which is an API that your website might consume to automatically detect fraud as part of an online journey for a consumer. But on the other hand, you might need a much more visual interface that's helping a fraud litigation team evaluate and manually review cases more quickly. And there, the product design thinking is much more important to make sure we can expose the model complexity in a way that's meaningful for those people in their roles, making those crucial decisions, and is integrated into their workflow. And then coupling those skills again with a sort of product mindset that combines technology feasibility with business priorities. And really what that product mindset does is all about maximizing value. How can we get something that's delivering impact quickly, and then how can we start iterating on that? So our product teams combine all of these different skills to deliver these high-value products. And the way we work, as I say, it's all value-based. So our first phase, we call our prime phase, is really where we try and identify the value. And obviously today we've been talking about fraud detection, but whether you're in insurance or other related fields, often there are other applications of analytics that can be applied across your value chain that can really drive performance. So when we talk about value, we're looking at things where we can improve cost or time or quality, real metrics that affect the bottom line. And the way we do that is we have quite a structured process inspired by the Google Design Sprint. We call it a SparQshop. And it's really about identifying those high value cases and sort of performing some acid tests around viability and suitability for machine learning. And then once we've identified where there's value and we've sort of done a back of the envelope estimation of the value at stake, we know it's worth proving. So that's when we put into our prove phase and develop those MVPs that Gareth talked about to actually demonstrate that, yes, you have enough data to build a model. We can build a model that's accurate enough to be useful. There's enough signal and noise in your data, and that actually we can create an endpoint that can be consumed by your business in a meaningful and operational way. And then once that proof phase has quantified the value, then it's all about continuing to capture and sustain and scale that value creation. So doing what's necessary to make that MVP more robust and deployed in your organization to really make that solution scalable and sustainable. And of course, then we would support and evolve that with you. So I'd say that first point is this SparQshop phase where it's working with you to really identify where those high value opportunities are and give both sides confidence that there's value at stake to be had there. As I said, to answer the question on the commercial model, we want to tie as much of our fees to performance as possible. So being clear on the value at stake up front allows us to be much more creative and incentivized jointly with you to make sure we're building products that really do make an impact. So if you would like to know more, feel free to get in touch. My details are here, and we'll follow up afterwards with an email and this content. So we can move on to questions if anyone has any further questions.
Yeah, I think we addressed the ones that were asked during the session. So, one new one: what technologies do you use to build these solutions, and does it require cloud? So we use a bunch of different, typically cloud technologies to build these. We're cloud platform agnostic, so we can build them in any of the major cloud vendors. Cloud is our preferred platform because it really is based on that elasticity kind of discussion, but also the tool sets, the platform tool sets in the cloud analytics platforms allow us to build these in a much more sort of robust, repeatable way, rather than trying to manage all of the different components separately. in a data center. So cloud is the preference, but we're very conscious and careful about security. So we do have a lot of in-depth discussion that we should talk to you about certifications and whatever else offline. But we do take security and update it very seriously. So we can probably have a more detailed conversation on that if that's a concern. I know that sometimes in the industry that's one of the concerns. And
typically we find increasingly it's multi-cloud solutions, or it's a combination of cloud and on-premise. Each organization is on a different point of the cloud maturity spectrum, and will have different strategic directions and regulatory concerns they want to mitigate against. And so actually, if I look across the work that we've done in this space, almost always there's more than one cloud partner involved, because our client is maybe working with one or two already, and increasingly the cloud providers are compatible. You've seen Google's announcement at Next last month. The Google Cloud business is expecting their customers to be using multiple cloud providers, so that interoperability between cloud providers is no longer an issue. And equally, using some aspects of the solution on the cloud coupled with some aspects of your solution on premise is also very easy to do. So we'll take into account what your appetite is for doing things in the cloud, and what regulations we need to adhere to make sure we've got the most appropriate solution, and taking advantage of the cloud where we can.
Yeah. And then if you lift the hood a little bit, we're coding the machine learning models in R and Python typically, which give us access to all those awesome open source libraries. We are then using container-based deployments, because that gives us the best portability and flexibility in deployment, and then running them, as we said, exposing them through API frameworks. So a combination of that sort of setup is what gives us the flexibility and also the resilience that we need. Any other ones? Any other questions? Where we're probably over time, are we? Yeah. Okay.
Good. Well then, thank you all for spending the time with us today. I hope you found that informative. We'll be following up, as I say, with all the materials. This will be linked to from our website. We'll send you the content of the webinar if you want to share it with colleagues of yours who couldn't make it today. But all it remains me to say thank you very much, and enjoy the rest of your Thursday. Thank you, folks.